in functions, etc., of course, is a very important idea. That's not the point. The point is, they learned nothing. I'm going to repeat it. The purpose of the activity was not to get 40 little facts correct. The purpose was to learn about inverses. Well, those children, due to, I think, classroom culture, did not expect to find pattern. Therefore, they didn't look for pattern. Therefore, they didn't find pattern. Therefore, they learned bugger all. Nothing. Okay, so again, I could really push the point that it's never the activity that is a good activity, the exercise, activity, task. It's never a good or a bad activity or task. It is the whole attitude and classroom culture that will decide what kind of learning which children will have. Some will learn nothing and others will. Okay. I had 3, 4 more, but that's just, again, I'm just pushing the basic idea. That children's beliefs influence what they learn just as much as intellectual factors. I just now want to jump sort of slightly on the topic and say, of course, we can discuss this whole thing in terms of the famous intended curriculum, implemented curriculum, achieved curriculum. And through all the years, we guys, yes, I admit, most of the time we took the intended curriculum as a given, wonderful thing, product, and then criticized the teachers of not properly implementing the implemented curriculum. But what Kuno is doing is saying, but maybe the intended curriculum is not so great, if I understand him correctly. And I think we should take it to heart as well. Personally, I think that it will be much better if the intended curriculum includes why and heuristics and big ideas and not the precise small fine print 2-digit numbers by a 3-digit number, which is now defining what happens. Let me show. Well, I first must, my favorite quote from Bibi. The black dot that lurks at the bottom of every honest pedagogue's heart is not so much whether he's teaching correctly as whether what he's teaching is worth teaching at all. Now, the real danger is not that we shall teach the right things inefficiently, but that we shall teach the wrong things more and more efficiently. And my dear colleagues, we are there. We are there. We've got whole workbooks full of column addition and multiplication, etc., and fighting which method to use, etc. And now we say the children don't understand it. Now we're going to try something more. But is it the right thing? Now I brought this quote under my arm from 1984 from Australia. Rousseau says, "The more explicit I am about the behavior I wish my students to display, the more likely it is that they will display the behavior without recourse to the understanding that behavior is meant to indicate." Now we know this expression. The more likely it is that they will take the form for the substance. In other words, that they do not understand the underlying concepts. And now we think we're doing a good thing by so accurately and specifically writing up the details of a 2-digit by a 4-digit, and in that grade they must do a 6-digit number by a 4-digit number. And well, that's all they learn. That's all they learn. I decided that I want to just share with you a little structure that we use that I think is very, very important, that I think must be part and parcel of every child and every teacher's arsenal of ideas about mathematics. It's very simple. Namely, we say that a calculation, all non-counting calculations, involve 3 phases, which I just briefly illustrate with 8 times 23. Well, I say transform, you can say translate, rewrite. I like my transform. We transform the numbers to more convenient numbers. What will that mean? Well, let's find out. I first read through. Then we transform it into a few simpler equivalent tasks. Easier, equivalent, all important ideas. And then comes the computation. So the computation really comes in here, and in this case, we already know what 8 times 20 is 160 is easy, etc. Now the reflection on this can be so important because we have, maybe I should just flash that. In order to do that, we need these different things. You need a good number concept in order to do something like write 23 as 20 plus 3. Okay. Then you need to understand properties of operations, in this case the distributive property of multiplication over division, multiplication over addition. And then what we call primitives, maybe you call them tables or basic facts or mental arithmetic stuff. It's the stuff that children must know by heart. Now, I say, is this the best thing to do? Is to now specify the number concepts separately in the curriculum and the number properties of operations separately and the primitives separately, and they never meet. As usual, we're not doing mathematics. I think that this whole scheme should be part and parcel of what every child should learn. As a matter of fact, Polya called the heuristic, or call it a problem-solving strategy. There is nothing more in mathematics education in the primary school than understanding that if you get a difficult problem, you try to change it into an easier equivalent problem that you already know how to solve. I think that basically that is nearly all that we do in just about the whole of school mathematics. But have you taught this thing? Or is it part and parcel of every day in a class of 5, 6, 7, 8, 9, 10 times? If we let children not say, and then I did this, and then I did this, why did you do that? May you do that? I decided I'll do 2 more. I'll just jump here and let's go for, just to illustrate, let's do something like 28 plus 35. The point is, we do not do this. Maybe if you count all or count on, you do the original thing. In all other cases, we do not do the original thing. We transform it into some simpler forms that we can do mentally without thinking. Recall. Okay. So, of course, we can do it in many different ways. For the moment, just to illustrate again, I'm going to say 28 is 20 plus 8, and we're going to say that 35 is 30 plus 5. So we are testing this whole place value or whatever. But then we're not gonna do 28 plus 35. We're gonna say 20 plus 8 plus 30 plus 5. And then maybe, just for you, I'm gonna say it's 20 plus 30 plus 8 plus 5. Is that okay with you? Okay, and then I'm gonna calculate. Then I'm gonna say, 20 and 30 is 50. Walk over. 8 plus 5 is, I'm in a hurry now, so. And all of this we call primitives. You must be able to do this mentally. Poof, poof, poof. Just like that. And it went so easy here in the end Because I chose so well in the beginning. You follow that? This is not step 1, step 2, step 3. That is the big problem. There is no step 1, step 2, step 3. What we are doing is you have something it's difficult, you change it into an equivalent form. That one is still difficult, you change into another thing. If you solve an equation, then each line is equivalent to the previous line and is sort of simpler. And you go on until the solution is obvious. Last step, x is 3. It's an equation. The solution is 3. You're finished. Okay, we could choose other stuff. Of course, I would love to do 30 plus, not 28, but write it as 30. I just want to push that that it is not step 1, step 2, step 3. As a matter of fact, the last step, number 3, comes first. Let me illustrate. I'll just take a new page. You know what is written here. Let's do 96 divided by 4. You have 96 sweets. You share it equally with 4 children. Well, now you do that in school. Now you'll see who's who. Namely, for those who are gone into automatic and do not know what they're doing, we have been doing now for weeks addition and subtraction, and they worked wonderfully well with this decimal decomposition place value, and therefore it will not be surprising if the children say, they're going to say 96 is 90 plus 6. It worked after all. It worked so wonderful for all those addition stuff. Oh, good. Of course, it's true. But the question is, so what? so that's step 1. Change the numbers. Okay, now change the task. Of course, we are now wanting to not do 96 divided by 4, but to change it into some smaller calculations, which in this case, I will now just have to write it like this, which we're really going to replace by this. I hope you agree with me. Well, you see, discussing this is heavy mathematics. Okay, here we go. That was step 1. Sorry for that. Step 1, step 2, step 3. Step 3, this is now when I have to write down the calculations. Great. Oh, gosh. What the hell? Well, I must say, I have seen clever children here. Sorry, I got lost for a moment. I was going to say here in Stellenbosch, sorry. But I've seen children who can do 6 divided by 4 is 1.5. They can do it, it's clever. But mostly children are stuck. Well, that's it. That is it. They're stuck now, they don't know what they're doing. Because why did you write it like that? You must actually be anticipating that you see a mile off beforehand that you are going to add 20 and 30 easy, and going to add 8 and 5 easy. If you didn't anticipate that, then you don't know what you're doing. Okay, so likewise here. So this is not going to work. Now make my day. How about a better method here? Or do you want to do it by long division? Well, it will be interesting what happens in long division. Huh? 96 divided by 4 goes in 2 is 8. Okay, I say nothing. Going. Well, come on. We're not going to say 96 is 90. Well, different people should actually be saying different things because it depends what you know for what I call primitives in step 3. If you don't know, so I'm going to say 96. I wanted to change the color. 96 is equal to 80 plus 16. And then I'll rush. The second step is 80 divided by 4 plus 16 divided by 4. But I would only do it if I know what 80 divided by 4 is. Are you with me? If I didn't know what 80 divided by 4 was, I shouldn't have chosen it. Then it would have been better to say something like 20 plus 20 plus 20 plus 20. Of course, then everybody complains it's too long. But I know that 20 divided by 4 is 5, so it's 5 and 5 and 5 and 5. Not so? Okay. Is this enough? Can I leave it? I hope everybody got that. You saw that it's really anticipating the third step. So there's a hell of a lot of know-how and skill in this. But our children can do it if we give them the right classroom atmosphere where we share our ideas and discuss these ideas and say, why did we do it? Why did we not do it? And you'll always get more methods. Of course, I still have one bright spark that says he's going to change 96 into 100 minus 4. You know, what's it? Just because I know what is 100 divided by 4. And just because I know what 4 divided by 4 is 1. So, again, I don't quite know what to call this. I probably would want to call it algorithmization. Make the verb from algorithm. I need a verb from algorithm. I wrote about it somewhere, but I can't remember how to. Okay, yeah, I don't want to unpack it too much now further, time's running, but I cannot, this is such a powerful tool. I wanted to show you, but I'm going to hide behind time again. Namely, it's difficult for teachers to identify children's methods. But once teachers understand this idea of how did you break up the numbers, what transformation did you use to make it easier, you sort of start seeing it a mile off. If you just search for how did you break up the number, then it's much easier to understand children's methods. So I would want this in the curriculum as algorithmatizing and part and parcel of serious activities with teachers in activities in school discussion and training. Okay. Huh? Okay. I go back here. I decided I'm going to flash even a few more. My students always called me a flasher. Okay. Here, I'm going to show you a few solutions of visual stuff from 18 times 5. I take it out of Joe Bowler's new book, Mathematical Mindsets, just because it's so easy and because it's so nice. So I'm just going to flash. So how to do 18 times 5. So this is not my work or my children's work, straight from Joe Bowler's book. Neil did it like this. I hope you can see my steps now. What was broken up. In this case, the 18 was broken up into 9 plus 9. Now, I'm not so mad about the concrete, or the visual or whatever, but for the purpose now, it's okay. As a matter of fact, it's quite nice in this context. Of course, provided you understand multiplication as an array or an area of a rectangle or whatever. There it is. Okay, now, of course, you must know what is 9 times 5 and 9 times 5, and you must do 45 and 45 in your head. That's what we do. Okay, and here is Ricardo. Man, I tell you, don't you just love Ricardo? So he's actually changing 18 times 5 into 9 times 10. And times 10 is our easy stuff, no? You can all multiply by 10. Heavy mathematics, 18 times 5. So it's like, we call it compensation, not so? I could, like my grade 5 class just now, I could divide by 2 and multiply by 2, not so? That's all that happened numerically. It was divided by 2 and multiplied by 2. But look how visually, how nicely it's moved that little box, and now you can see it as 18 times 10. And just think, well, when I wrote it down, I thought to myself, man, would I have loved to be in class with this, because, you know, I would immediately say, but isn't it surprising how, you know, why would, sorry, I thought I would just, why would 9 times 5 plus 9 times 5 be the same as 9 times 10, you know? And it's so easy because, of course, you must see 9 times 10 is 9 tens or 10 nines, etc. So that is 9 fives plus 9 fives, or 5 nines plus 5 nines. Well, 5 nines plus 5 nines is 10 nines, not so? Hey, hey. Now I must just get rid of the pen. Okay. Now we do a few quickies. We got that. This, just to understand, what did he do? He split the 18 into 10 and 8. Okay, and there is the split. Very straightforward, but very easy, not so? Ariane again split the 18 into 15 plus 3. Now can you see, if you go into automatic, then you will always want to say 18 is 10 plus 8. But it depends what you know. So this guy only did this because apparently he knows that 15 times 5 is 75. I also know it. And Brian. I changed the order actually. Now, Brian is my kind of guy. It seems to me he was not so confident that he knew the stuff, so he took it in small little steps. 2 and 2 and 1. So he split the 5 into 2 and 2 and 1. And if you've got anything to do with any primary school, you must know that children know the doubles better than anything else. And so there you got it. 18, double 18, 36, double 18, 36, 36 and 36, double again, 72. What a walkover. Plus 18 is 90. And of course, is it Jamie? Like my 96 is 100 minus 4 just now? You see, if you get the calculation and you get something like, it can be done. I taught a grade 4 class for a whole year. He's a total disruptor. Yeah. Okay, we'll compare the methods, etc. Now the great thing is, Peter and I use the word children's autonomy, and I'm not getting to it. And I say, we think it is absolutely important that these are not taught, but that children have, that is expected of children not to develop just one, but several of these, and to discuss them and show them and to explain them to others. And then, if the child had to do one, to be free to choose his own one. Maybe it's not as short as another one, they say, but I understand it better. Okay, then he's got the autonomy, the independence to do what they want. Okay. Right. I think I must skip it. Piet, help me, how much time left? Hoeveel tijd, Piet? I'm skipping this. Okay. Good. I might go back to this.